All right, so we just finished our lecture on definiteness, which is really a dissection of the theory of quadratic forms. Remember that quadratic forms are represented by real symmetric matrices. So there's this sort of dictionary between the world of quadratic forms and the world of real symmetric matrices. If you give me one, I can tell you what the other is. And I've written two pieces of code which accomplishes that. In this first piece of code, if you input a real symmetric matrix S, this will give you the quadratic form represented by S. So let's click Evaluate. So the matrix that I've predefined is this real symmetric matrix. And again, how is this matrix related to a quadratic form? Well, the formula is the quadratic form is the inner product of the variable vector with this matrix S times the variable vector. And in this case, I get my whole quadratic form here. We have all these terms. We can look at one of these terms, maybe 2 times x1 times x3. What that's telling me is that half of 2 is in the 1, 3 position, and the other half of 2 is in the 3, 1 position. So in the 1, 3 position, I should have a 1, and in the 3, 1 position, I should have another 1. In this second code cell, here, what we can do is we can write down a quadratic form, and then given the quadratic form, we can extract the real symmetric matrix representing the quadratic form. Now, in order to do this, I need to start by initializing my variables in the system. So I'm going to use the variables x1, x2, x3, and the syntax for initializing the variables is var, open parentheses, open single quote, x1 space x2 space x3, close single quote, close parentheses. That tells Sage that x1, x2, and x3 are variables. Now I'm defining my quadratic form. This is q equals 3 times x1 squared. Again, the syntax in Python for squaring is double star. Then we have minus 7 times x1 times x2 plus 11 times x2 squared minus 4 times x1 times x3 plus 2 times x2 x3 minus 19 times x3 squared. So so again, I've input q here, and if I click evaluate, the code should extract the matrix representing the quadratic form. So I get my real symmetric matrix here. Let's just verify that this makes some sense. Let's see here. We had negative 7 times x1, x2. That means half of negative 7 should be in the 1, 2 position. So I get a negative 7 halves. And the other half should be in the 2, 1 position, negative 7 halves here. So again, the first cell gives you the quadratic form given the symmetric matrix. This code gives you the symmetric matrix given if you provide the quadratic form. And again, you can mess around all you want with this. Let's say you had a quadratic form on like 4 variables. You'd have to initialize the 4th variable, and maybe you want to add some terms here. Plus 18 times x1 times x4 minus 27 times x3 times x4 plus, I don't know, 79 times x4 squared. If I evaluate now, this gives me the real symmetric matrix corresponding to my new quadratic form. So feel free to use this. Hopefully you find it useful.